All right, so up to this point, what we've discussed about inverses is the simple idea of switching x and y values. We did that in tables, we did that in graphs, we did that in equations. But I'm pretty sure you guys are also familiar with an inverse in a different aspect, okay? You've heard of inverse operations before. So for instance, if I added 3 to a variable, what would the inverse of that operation be? Yeah. Subtraction of 3. Okay, so inverses, another way to think about them is that they undo each other. An addition of 3 can be undone by subtracting 3. Okay, it kind of cancels it out. Same idea as if you were to multiply by 3, you could cancel out that concept by using a division of 3. Okay, those are inverse ideas. So we're going to take a look at that idea of an inverse today. How can we cancel things out? How can we undo some things? We're going to see how that kind of works. So on page 110, we have a g of x equation at the top, okay, kind of the original equation, whatever you're starting with. And we're going to explore some different things here. The first column wants us to find g to the negative first. Now we've been discussing how that notation means inverse. So if we're going to find the inverse, we're going to switch those variables, and since we're dealing with an equation, we'll have to solve for y. So this is going to be kind of good practice for us from yesterday. F of x, g of x, h of x, whatever they give you, we know that means the same thing as a y variable. So if you were to switch the x's and y's in this equation, we would have x equals 3y minus 4 over 2. I think we can do that simple step, right? We can change x's to y's and y's to x's. The tricky part, though, comes in the process of solving for y. And this is when you have to use those inverse operations. So how might you want to solve for y? Can we start to move some numbers to the other side? Yeah.
Multiply by 2 on both sides.
Perfect. Okay, so notice how on the right-hand side we are dividing by 2. To undo that operation, we would have to multiply by 2. And we'll multiply by 2 on the right-hand side to cancel out that division of 2. Oh, sorry, we'll multiply by 2 on the left-hand side to cancel out the division of 2 on the right-hand side. Can we keep using some inverse operations, moving some terms? We thinking add 4? Okay. And lastly, we can divide by 3. So when you divide the 3 over, you got to divide the whole left-hand side by 3. So you could leave it like that. Does anybody rewrite it in a different way? Just out of curiosity. Maybe you've seen it like this. If you divide the 3 over, you have to divide the 2x by 3, but also the 4 by 3. So this could be 2/3 x plus 4/3. Like if you do each division separately. Have we seen that before? Maybe. So it really doesn't matter which way you represent it. Okay, they're both technically mathematically correct. So if this is what we get after we switch the variables, this is what's representing our inverse. We're going to go ahead and label it appropriately. So either one of these answers or representations would be fine. Okay, one concept of an inverse is simply just switching the variables. Okay, so now that we've found the inverse, let's go ahead and check out the other 2 columns. In the next column, we have some funny notation going on. What do you think that's asking us to do? Can you tell by the way it kind of looks? We've seen this before, just not necessarily with an inverse. Go ahead, Addison.
Plug in the inverse of g of x into x.
In the g of x equation. So we're going to take the inverse equation, whichever one you're more comfortable with, and we're going to plug it in for the x in the original g of x equation. Do you see how based off the way that's written, the inverse is on the inside, meaning you're going to plug it in? Okay, so do we have a preference as to which one we use here? First one, I heard second. How about you guys use whatever one, okay? It still should work out regardless, okay? So let's check this out. We're going to take one of these, either one, and plug it in for that x. So we need, first of all, the 3 out front, that coefficient, and then in for the x, choose whichever inverse you want to use. I'm going to go ahead and use the first one, but again, it doesn't matter. If we continue through the g of x equation, we need to subtract 4, and all of that's over 2. So we're going to simplify this. We're going to see what happens if we were to plug the inverse into the original. Okay, you're going to see some neat things happen. Anything you guys notice? Yeah?
We're multiplying by 3 off the top, so those would cancel out.
Okay, so notice how we have a multiplication of 3 and a division of 3. Those are inverse operations, meaning they cancel each other out. They undo each other. So we're left with the 2x plus 4 from the numerator. We still have the minus 4 on the end, and all of that is still over 2. Anything else going to happen? Any other inverse operations showing up that's going to cancel each other out? Go ahead, Kyle. All right, those are inverses. They cancel each other out. Any other things going to happen? Yeah?
I would divide by 2.
All right, the division of 2. Notice how the 2's being multiplied up top by the x, and we have a division of 2 on the bottom. Those are inverse operations. So in the end, all we're left with is x. So if you take a look at this, if we plug the inverse into the original, notice how it undoes everything. Okay, it cancels out all of those numbers in there, all of those operations that you're doing, and you're just left with the single variable of x. Okay, that's if we plug the inverse into the original. What if we were to do the opposite? Okay, do you see the third column, how it's very similar but just switched? This time we're going to plug the original into the inverse. So we're going to take this equation at the top and plug it in for the x in either inverse equation you want to use. Okay, again, it doesn't matter which one, it should work out either way. I'm going to go ahead and use the first one. So I have the 2 coefficient out front. In for the x, we'll plug in the g equation from the top. I still have the plus 4, and it's all over 3. Okay, I'm using that first inverse equation we had. But it doesn't matter which one. It kind of has the same setup as the one we did before, so maybe we can use some similar ideas there. Notice how the 2's would cancel. One's being multiplied, one's being divided. Those are inverses. We have a subtraction of 4 and an addition of 4, so those cancel out. Those are inverses. And lastly, notice how the 3's would cancel. One's being multiplied, the other one's being divided. So those are inverses. We get the same x out, right? So it really doesn't matter which one you test, we'll say, whether you plug the inverse into the original or the original into the inverse, okay? If they're truly inverses or opposites of each other, they will undo each other. They'll get rid of all those numbered values. So this is presenting us with a way to test to see if 2 equations are inverses. Do they in fact undo each other? Okay, get rid of all those numbers. So just as in your notes, something to reference, it doesn't matter if we plug the inverse into the original or the original into the inverse. As long as we undo all the numbers, meaning we get x out in the end and just x, we know that the two equations undo each other, meaning they're inverses. Okay, so we're going to test this. We're not necessarily switching variables anymore and solving for y. We're testing, is one equation the inverse of the other? Meaning, does it undo it? Okay, undo all those numbered values. Okay, so let's take a look at the first one. Determine if each pair of functions are inverses of each other. Okay, would they undo each other, cancel out all the numbers? So it doesn't matter which one you put in where. Do we want to put f of x into g of x or g of x into f of x? Do you have a preference? It shouldn't matter. I'm just wondering which one you guys want to do. Do we want to put the fraction in for that x or this linear into that x? Yeah?
Put f(x) into g of x
Okay, so we'll take that equation and plug it in there.
and offset
Yeah.
these ratios.
Sure. Okay, so mathematically speaking, we are going to plug the f of x equation into the g of x. So that would be g of f of x. Notice how the f is on the inside because that's what you're plugging in. Okay, so in for that x, we'll substitute in the 2x plus 3. We still have the minus 3 on the end, and it's all over 2. Let's simplify it. Let's see if we can actually cancel out all the numbered terms. Don't force it, okay, because you know what you should be anticipating. You're trying to see if you get an x out, but don't force it because sometimes maybe you're not able to cancel everything out. Can we simplify it? Yeah, we have a plus 3 minus 3. Those are inverses. They undo each other. Multiply by 2, division of 2, those are inverses. Those undo each other. There's how we just get x out. So it says determine if each pair of functions below are inverses of each other. What do you think? Do they undo each other? Do they cancel out all those numbered terms? Yes. Okay, so yes, f of x and g of x are inverses. So what this is signifying, what this is telling you, is that if you were to switch the variables in one of the equations and solve for y, you would end up with the other equation. Okay, so you don't have to write this down, but I'm going to show you like exactly what that means. Which equation do you want me to use? Do you want me to switch the variables in the f equation, or do you want me to switch the variables in the g equation? You want to pick one for me? You want to do f? Okay. So if we were to switch the variables in the f equation, remember f of x and y are the same thing, this would be x equals 2y plus 3. Okay? Solve for y. We can subtract the 3 and divide the 2. Isn't that the same as g of x? Okay? So when I do switch the variables in this one, I do get this equation, which means this is the inverse of this. Okay? So we've been doing this process so far to actually find the inverse, but if you just want to determine, like yes or no, are they inverses of each other, you can simply plug one into the other one and see if all of the numbers undo each other. Okay, it's a way to test to see are they inverses, not necessarily to find the inverse. Those are two different questions. Okay, so let's go ahead and try another set. Are these two equations inverses of each other? Do they undo each other, meaning canceling out all those numbered terms? So, do you want to plug f into g or g into f? Doesn't matter. Yeah.
G into F.
You want to go the other way? Okay. So if we're going to plug g into f, we need f of g of x. Okay, g's on the inside because that's what you're plugging in. So we would have 2x plus 1 all over 2, and then minus 1. right, let's see if we can simplify this. In this fraction, do you notice how you have two terms up top but only one down below? So in the fraction, that's symbolizing that you need to divide each of those by 2. Okay, you can kind of break up that fraction using that kind of technique. So this would be 2x over 2 plus 1/2. Have we seen that before, or does that make sense? Okay, and then we would still have the minus 1. Are we all adults in here to some degree? Maybe? You'd say so? Okay. I'm just going to show you a way of how I remember this. Okay? We're all adults. I'm assuming we're all adults. Okay? That means something different in health class, right? Okay. In this room, though, okay, that stands for single term denominator. Do you see that? Okay. So whenever you have a single term denominator, you can break up the numerator. Do you notice how when I did that, it kind of formed a heart shape, right? So let's face it, if you have an STD, you might break some hearts. Do we get the connection? Okay, so STD means something different in health class, okay? But in here, it's a single term denominator. You can break hearts, meaning break up that fraction using that single term denominator. Do you think you guys remember that? Yeah, we're adults, okay? I'm not going to get any parent phone calls tonight, am I? Maybe? Okay. Again, it's something different in health class, but it's single term denominator in here. Okay. Do we see any simplification, any inverse operations that we can use? Cancel out some things? Yeah.
2x divided by 2.
All right. That's just going to be x. The numbers, though, we have 1/2 minus 1. So that would be a negative 1/2. Do we have any other inverse operations that can undo each other? Unfortunately not. Okay, so if this is the result we are left with after we plug one function into the other, are we able to say that they're inverses? Do they cancel each other out? Not completely, okay, because we still have a numbered term left over. So for this one, we would have to say no, f of x and g of x are not inverses. Okay, so two big concepts for inverses. You can find inverses by switching x's and y's, okay, and kind of simplifying from there. But you can test if two functions are inverses of each other by seeing if they undo each other. Okay, that whole inverse operation concept. They cancel things out. Are we okay with that? Other aspect of an inverse? You're used to that. Addition undoes subtraction, multiplication undoes division, squares undo square roots. We're used to those. Okay, those are technically inverses as well. Okay? That's it for inverses. I think it's been going really well. Are there any homework questions that you guys want to go over? We still have a few minutes. Just thought I'd ask. Yeah?
Number 7 on page 112.
Oh, this is a good one. Well, you want to do number 1? I'll circle them. We want to do 7 together. Any other ones? Maybe some other ones will pop up. Okay, let's check out 7. Did we talked about graphing that the other day, right? Okay, and we developed kind of that asymptote graph, I think. Okay. Can you determine if that graph is 1 to 1? We got to test that first to make sure an inverse exists. Is it 1 to 1? Uh-huh. Okay, so f of x is 1 to 1 because it passes the horizontal line test. So therefore, we know it has an inverse. Okay, you are able to switch the variables and solve for y and develop some new function, some new relationship. So we're actually going to go through and do that. Now what's a little tricky with this one is when you do switch the variables, you get x equals y minus 3 over y plus 2. Do you see how you have two y's in this equation? Our goal is to eventually solve for one y. So we're going to have to be a little strategic, a little tricky here. We have to eventually turn two y's into one y. So we'll get there in a second. Is there anything you guys feel like doing from there to simplify it, rewrite it? Keep in mind we're trying to solve for y. Personally, I think fraction work might be a little tricky sometimes, yeah?
Multiply both sides by y plus 2.
Yep, we'll multiply the denominator over, okay, an inverse operation. Instead of dividing by y plus 2, you can multiply it to the other side. Maybe we'll distribute it in the x, okay, get rid of those parentheses. Are we okay so far with the algebra? Not too bad? Okay, so here's the tricky thing. Keep in mind, our goal is to get y equals. We want the y variable all by itself. We have two y's. So let's be a little strategic. What if we were to get all the y's on one side of the equation, because really that's what we're trying to solve for, and we'll get everything else to the other side. So for instance, if this is a y term, let's subtract this y over, that way it's on this side with this y term, and since the 2x doesn't have a y, we'll subtract it to the other side. That's algebraically possible, right? We're just moving around some terms. So we'll subtract the y to the left, and we'll subtract the 2x to the right. Just doing a little rearranging. Okay? So here's the magic part, okay? On the left-hand side, we have two y's. How can we turn those two y's into one y? Do you see it? Yeah.
Y, and then parentheses x minus 1.
Okay. You can factor that y out. Isn't it a GCF? It's a common factor. It's a common term in both of those pieces. Does that make sense? Do you see how they both have a y in common? So you can factor it out. There's the magic. That was changing two y's into one y. So now that we have one y, how can you get it all by itself? Yeah. Divide by x minus 1. So there's your inverse. We'll label it appropriately. That one was a thinker. But I'm glad we brought it up. All right. Any other homework ones that you want to discuss, go over? No? All right.